Well, good morning, ladies and gentlemen. Great to see all of you folks this morning. 9 o'clock way out here by the airport. I was worried about, all the strike actions and various shenanigans, what that would do to the attendance. But it looks like we're doing pretty well. So thank you so much for coming. My name is Chris Meyer. I teach physics at York Mills Collegiate here in Toronto. And I'm also Vice President with the Ontario Association of Physics Teachers. So what I would like to share with you today is the work that we've been doing teaching electricity, the topic of electricity, through inquiry and simulations. Now, I want to start off with a question for you. So please, there we go, find your multiple choice letters. Now, there's baskets on each of your tables. These are similar to the baskets that I have in my classroom. And there's 3 cards per... There's 3 cards per basket. So is everybody okay? We have the cards there? Excellent. So, first question for you. When I give my presentations, it's very helpful for me to know about my audience. So, here is my first question for you. Pick your favorite one. And hold those up, please. Nope. Hold those up, please. Okay, thank you very much. So it's quite a cross-section, but definitely lots of A's. And that might be the majority response. That's good, that's good. A few people selected E. And I'm not sure what rumors are circulating, but we are indeed serving a special kind of food today. Food for the mind. Because what I want to touch upon today are 2 important parts of teaching. One is content mastery. To be successful teachers, you have to feel confident with your understanding of the content. And pedagogical expertise. So what are the right learning strategies to use? And if you put the delicious chocolate and the tasty peanut butter together, you get that most awesome of creations called good teaching. Notice it's already been munched on. So this is what I'm hoping to do today through our workshop together. Now our main theme is learning by inquiry and also learning through simulations. Now, can I see a quick show of hands? How many people have brought a laptop, have a laptop with them this morning? Yeah, it needs to be a device that runs Java. So generally the tablets, Android and iOS, don't do the trick. Okay, so, sorry, just one more time. Do we have one per table? We're close. We're close. I think we might be able to work it just so we do have a chance to try at least one short thing together. All right. So, inquiry-based learning. Let's take a look at how inquiry-based learning works. One of the main parts that allows this style of learning to be successful is structured group work. So in our classes, we have our students assembled into groups of 3, and they have been assigned and trained in a variety of roles. So one of the roles is the manager of the group, help to organize your group. Another is the recorder in the group. So we use whiteboards in our classroom, so they'll be the official whiteboard writer. And they also help to check their neighbor's written work for accuracy and completeness. And then each group has a speaker. So if I need to hear from a group, and I call on that group, they know it's their job to talk to the class. And also, just to help read through the questions that the group is working on together. And these are the roles that you're about to take on in just a moment. So I have brought in, so you should find these on your table. So it's the second page of the handout that I have. Now I put 3 per basket. So I think we should have enough for... Everybody's got one? Looks good. And so when my students start the topic of electricity in grade 11 physics, I take them all the way back into the core ideas of grade 9 as if they had never seen them before. And this is one of the reasons why I think this set of lessons that I'm sharing with you could be very useful for you in your grade 9 classrooms as well. So this is their introduction to the topic of electricity. And what we're going to do is take about 10 minutes for you and your group members to begin to work through this investigation together yourselves. And you'll get a glimpse of what this type of inquiry lesson looks like. You'll get to try out a little bit of an experiment in your baskets. You should have a baggie that contains a few electrical items. And these are the first parts of their investigation. So what I would like you to do is introduce yourselves to your fellow group members. So if you can roughly organize yourselves into groups of 3, that works best. Choose a role. So just pretend you're students for the next 10 minutes or so. And work through the first bit of our investigation. And then in about 10 minutes we'll stop and we'll talk about what you've noticed, what you've gone through. So please introduce yourselves. Find your baggie of equipment and start your investigation. Ladies and gentlemen, listen up, please. So this is very much like the structure of my class. I will talk for maybe a maximum of 10 minutes at the beginning, but really I try to minimize that. 5 minutes, get them started on their activity. And so you guys made a great start today. It's awesome. And now that you've played a bit with the ball, it's very entertaining to watch the kids go through this first part of the activities. Even my grade 11s, you know, they've seen this all before. They spend a lot of time trying to get those bulbs to light up. It's very interesting to see. Now that you've had a chance to look at that part, with your group, just sort of scan through the rest of the investigation and try to get a sense for how I designed it. And in particular, think about this question: what makes this an inquiry lesson? And on your table, I have brought my travel whiteboards. I apologize, they are really crappy, but they are really light. So that wins in my books. So on your whiteboard, using large, easy-to-read print, jot down, just very briefly, a few ideas that your group comes up with. So why is this an inquiry-style lesson? All right, ladies and gentlemen, let's pause here. And again, this is a very common function in my classroom. The groups will be busy working away, then we'll stop for a moment, and it'll be time to talk about some of our ideas and share some results. So what I would like is the speaker for each group to just share one point that your group came up with. And it's very helpful if, when you do that, you hold up your whiteboard, or just have a neighbor hold up your whiteboard so that the rest of the room can easily see. So let's think, what makes this an inquiry lesson? So perhaps we can start with our group over here. Could you hold it up nice and high? Or maybe stand up and...
Sure. No method is given. So it's open-ended in that way.
Thank you very much. And we'll go to the back table. Who's our speaker there?
It's hands-on and experimental.
Thank you. Tommy's group?
This one? We said the students are doing the work, so the students are doing the work.
Thank you. Thank you. The far table here.
Try different things, and then the conceptual knowledge. One of the things that we really liked about was that we compare the cases that the whiteboard works, and then the other case that doesn't work. So that getting, if it doesn't work, that doesn't mean it's wrong. That you have to think about how to make it work.
Thank you very much. There's another group at that table.
It's open-ended questions, like so because they are trial and errors, they are going to figure out themselves what it's going to be work or not working.
Thank you. Thank you very much. We'll go to the middle table now.
We said things, but we said we're not told, students weren't told the answers or the information. They basically had to arrive at them themselves. But what was good is that the answers were given afterwards, like there was a little blurb in a box. So they still got it if they didn't catch on.
It's very interesting. Even by the end of the course, the students, they don't rush ahead to read what's in the box. They
Yeah.
think through the questions. This group over here.
Well, now I'm tapped, but we came up with there's no clear conclusion to be drawn from this. So drawing on the previous discussion that they're given a task, but there's not anything that they're specifically told that they're going to be ending up funneling towards. So different groups could draw different conclusions based on the way they set it up.
Thank you.
I'd love to echo all of your excellent ideas.
Great, and our grand finale.
More than one answer or multiple solutions.
Yeah. Okay. Thank you. So it's great. You've highlighted so many of the important factors or features of an inquiry-led lesson. So to summarize it, my summary goes something like this. The core idea that makes an inquiry-led lesson work is the constructivist learning philosophy. So students are building up the ideas first through experimentation, preferably, but if hands-on is not possible, they can still experiment with basic concepts as well. So toy models, toy mental models. You can ask them, okay, what does this little mental model do? So they play around with the ideas first, and then the ideas are given a name, then it's formalized. This is a very important part of building their own understanding of the idea. So they go from observations to theory. And what do you know? This models the scientific method so nicely. So inquiry-based learning is such a natural fit to what we are trying to do in our science classrooms. And did you do much math? In this whole investigation, there really isn't any math. You compare a few numbers toward the end when you start making some measurements from your ammeters. But the math is left at the end. And math for many students is a barrier or an obstacle. But what I have found from my experience is if they have enough time to familiarize themselves with the ideas first, then when the math comes around, the math actually has a meaning for them. They know why they're using it. And so many of those mystical features of mathematics are gone. So they can see why you need to use the math for this kind of situation. Now, another very important feature of inquiry-based learning is it helps the students and the teacher explore students' prior knowledge. One of the most important things that will happen if you try some teaching like this is you will begin to learn, perhaps for the first time, what's really going on inside your students' heads. And that's when, or that picture I showed you at the beginning, that's when the content mastery and the good pedagogy finally have a chance of coming together in the most effective way possible. So you get this wonderful opportunity to see what's going on in your students' heads. And for example, I know they're terrible. and for example, the whiteboards, these are very good for quickly sharing ideas amongst the classroom. But it's also very helpful for the teacher because I can walk around and observe the groups, and at a very quick glance, I can get a snapshot of what those groups' thoughts and discussions were. So it's very helpful for me finding out what's going on in their heads, in your heads today. And so they need to, as much as possible, make predictions about what they think will happen, because that cues their prior knowledge, and get them to explain as much as possible in their own words. So this helps students to sort through the ideas they bring into the classroom, and then they begin to understand better what the limitations of those ideas are, and why the new scientific ideas are better at describing the way our universe works. Now, I do see a number of people jotting things down, and I forgot to mention at the beginning that this whole presentation is available on my website, and the website information is given on the first page of your package there. So don't feel you have to desperately write something down as we're rolling along here. I hopefully do. They might be spread somewhere in the room, but I'll try to track one down for you. All right, so I just want to take a moment to talk about this dashing gentleman here. This is Eric Mazur, a physicist from Harvard University, and he was teaching his kids about the topic of electricity. And on the final exam, he gave them 2 questions about electricity. Now, these are the kids from Harvard, right? So you got to challenge them. So he gave them this weird-looking circuit and asked them to solve for, the potential difference and so on. So, score on the exam, 75%. So for this question, that's how well his students did. But he had this nagging doubt in his mind that the students really weren't understanding what they were doing. And so he decided, I'm going to put a second electricity question on the same exam. And what was different about it is it did not have any numbers in it. It had a realistic-looking circuit and a simple-sounding question. So what happens to the brightness of the bulbs and the voltages when you close this switch? Now, to the experts, a question like this is almost trivially simple. How could you put that on an exam at Harvard University? But he did, and the students' result on it was 40%. And this really opened up his eyes to understand better what was going on in his students' minds. So he realized that when the numbers disappeared, they have very little conceptual understanding to fall back upon. And that's when he realized that he had to change the way that he taught. So moving away from the traditional lectures to something that encouraged students to actively engage with the material. And our inquiry example is an excellent way of doing that. I have a question for you. Here is a circuit. So you can see we have 3 bulbs there, the cell, and a switch. Now, I don't want you to discuss with your neighbors at this point. I want you to think about it yourself. And here's the question. When this switch is closed, what will happen to the brightness of bulb A? So I just want you to take a moment to think about this on your own. And 4 possibilities. So the way that I train my students is, once you've selected your answer, select it on the multiple choice cards and put them face down so your neighbors cannot see. Then I know you're ready. So what will happen to the brightness of bulb A when the switch is closed? Okay, now I would like you to direct your eyes to the front. Please don't look around at your neighbors' responses. Exactly what I say to my students. And hold up your response cards. Okay, just keep them up for a moment as I do my mental tally here. Okay, please put them on the table face down. Again, your neighbors not looking at the answers. Okay, so I saw quite a variety in the audience's answers. And that's okay. That's what usually happens. And I'm not going to tell you the answer yet. Because when you're a scientist and you have a question like this that you need to know the answer to, what you do is you conduct an experiment. So how do we find the answer? Well, we want to build the circuit. Now here's where we get to the other theme for today's workshop. I came across this piece of research coming from Colorado University, and they were asking the question, can we replace the traditional hands-on labs with simulations of circuits? And they did an experiment. So they wanted to know, how would that affect students' ability to actually build real-world circuits? And in their experiment, they found that the students who used the simulation took less time to build a real-world circuit and to write about it than people doing the traditional hands-on labs and those who just had no practice at all with either. So using these simulations helped them build the real-world circuits. And when we give these students questions, just like the one that I gave you, so no numbers, just a conceptual question about how electricity and how circuits work, how did they do? So the simulation group, which is the lavender, the lavender bars there, they did better on all the questions, and often by a statistically significant amount. So based on this research, I thought, well, why not use circuits? Because as much as I personally enjoy, you know this, right? The mounds of wires, and how much time do you spend trying to find a wire that is not broken inside, trying to figure out if it's the bulb that's burnt out, the battery that's dead, or is it? You spend so much time with that. I thought, well, this is just perfect. So as you noticed in my introductory investigation, we do some hands-on. And the second part of it, if you look that far, they build a circuit and use an ammeter. But then after that, we move right into the simulations. And this is my main tool, the PHET simulations, also developed from the University of Colorado. And I think this is just a fantastic bit of software. It's drop dead easy. The first time that I did it with my class, as I was trying to explain things in the front of the class, the kids had it already set up on their computers and they were building the circuits. And, they left me behind. It's very intuitive and easy to use. And so, what I was hoping to do today, if we have one functioning computer at each table, is to give this a try. And then you can build that circuit that I showed you before. So you can build this circuit here and test our results. Now, to get the software, Google PHET and go for the circuits option here. And if for whatever reason the Wi-Fi is not being nice to you, I have it on a thumb drive here. And they are moving. Did anybody find the dog yet? Anybody find the dog? The dog is a highlight for many students. If you do try this out with your students, you will soon know what the dog is all about. I'll leave it at that. Now, whenever we bring technology into the classroom, there is always a set of headaches that comes along with it. In my experience, the headaches using this simulation are relatively small. The learning curve is very, very short. And so I have found it's just so much better than using the traditional batteries and bulbs. Even when the equipment works, the equipment does not follow the ideal patterns that we try to teach our students. And so even in that ideal case where things actually work, how often does that happen? They still have a lot of difficulty finding the patterns that we're looking for. So I have enjoyed working with the circuit simulation, and I know my students have as well, especially when they find the dog.
It was
You have it here.
Yes, sir.
Question. So, like students' learning of overall concepts with this stuff is a little bit better or a little bit faster. What do you think about the idea of them learning to just muck around with stuff and problem solve? Like saying, like, which wire is it? Is the bulb burnt out? Mm-hmm. Like, how much value is there in them actually learning the practicality of mucking around with electronics and electricity?
I believe it is a very valuable thing. The type of problem solving that goes into figuring out why this thing isn't working is really valuable. And that's why I do one real experiment with bulbs and ammeters and all the wires and so on. But after that, I want to get into the fundamentals of how electric circuits work. And the problem is, those challenges arise every single experiment that you do along the way. And I try to do a lot of them. So I found, the cost-benefit analysis of things, that this is a good balance. So they get a chance to play with the equipment, but when it's time to really focus on the patterns and extract the ideas, using the circuits, it just streamlines things so much. I wish I had more time for them to play around like that. But I try to make sure that they do experience the real thing as well. Yes, sir?
How about the alligator clips and little wires and stuff versus full scale with real lights and stuff like that?
I've never tried the home wiring kind of setup. So
we got one for C physics. We
right
there, and it's kind of neat. But I was wondering if we should do that for the same indicator noise also.
right, yeah. I know that's part of the grade 12 college physics course, the home wiring, but I haven't tried it myself. All right, so now, if you were successful in getting your circuit to go, and I'm sorry I couldn't give you more time for that, then you would discover that when you close this switch, what happens? The bulb becomes brighter, which for most students is very counterintuitive, and for many teachers is very counterintuitive. And that's the other part of today's workshop that I mentioned, is building up that content mastery. We're not all masters of these topics, but especially using the simulation, you have a great opportunity to very quickly play around with things and build your personal understanding of how electricity works. So, now, moving right along. So we've played with our simulations, and that went well. Now, another bonus of these simulations is it helps us to better illustrate what's happening inside a circuit. Now, I don't want you to answer this question. I want you to answer it on behalf of your students. So if we gave this question to your students, what response do you think they would choose? I won't put you on the spot again. What do you think your students would choose? So why don't you choose your multiple choice letters there? And this time we are allowed to look at each other's answers because they're your students' answers, right? And hold them up. What do you think your students would say?
What they would choose?
Yeah. What do you think your students would choose? Yeah. Okay, thank you very much. So if the students know that the electrons are repelled by the negative end of the battery, they'll say, oh yeah, the electrons come from the battery, they run the lap around the circuit, and they return back home, like a car leaving and returning to its garage. Right? But the simulation provides a much better way for them to understand what's happening. They will see the electrons present in the wire even before the switch is closed. And so the electrons are at every point in the circuit already. And then when you close the switch, they all begin to move. So like musical chairs, rather than the single car coming out of the garage. And again, that's a very valuable part of building your students' physical understanding of what's happening inside a circuit. And by looking at a wire, we just don't get a physical sense for what is taking place in there. You might have noticed in the inquiry investigation, we had the bare piece of wire. Did you connect that to the battery and touch the wire? Yeah, that often excites the students because they get a real physical result from what's happening inside the wire. They notice the wire gets really hot, or it's too hot to hold the ends of the wire onto the battery. Something's actually happening in there. And because electricity is so invisible, any of these physical clues are very valuable for building their mental model of what's taking place inside these wires. And I think this simulation is an excellent way of doing that. Now, another fantastic simulation is this one, also from PHET. So the good old static electric sweater. So this one I also use with... okay, it's not letting me find. That's fine. This one I also use with my grade 12s because it lets you see the allocation of the charges, move them around, and then you can see the results. So another excellent and handy simulation. One final simulation, which I show my students, is this one here. This is from an organization called concord.org. And I'm going to load this one up for you because it does something that the PHET simulations don't do. Now, if you download my PowerPoint, there's hyperlinks in there that will lead you to all of these things. So you don't have to worry about trying to track them down later on. But this one is the next step up in the accuracy of the physical model for... Oh, yeah, it worked last night. No. It's the next step up in accuracy for... Okay, well, I'll just show you the picture. Here we are. So in this simulation, you get to adjust either the temperature or on another screen it's the voltage that's applied to your wire. And what's illustrated here are the positive ionic cores that make up the structure of the metal of the wire. And then we have the electrons that are free to move within the wire. And you'll see a lot of the random thermal motion of the electrons depending on the temperature that you have. And if you apply a voltage, then that random thermal motion causes them to start to drift in one particular direction. And if it collides with an ionic core, it starts the core jiggling as well. So it starts to transfer the heat through the solid. So there's so much good physics in this simulation here. I find it's great when we get to the topic of resistance, and I want a clear picture for them. What's happening inside the wire when the current flows through it? And so I find this simulation is really good for that. So download the PowerPoint, you just have to click on this screen, and the hyperlink brings you right there. So that's another simulation that I regularly use. Now, one of the questions that I get when I'm talking to teachers about inquiry-based investigations is, how do you know if students get it? Because you're not telling them the answers anymore. So you may have observed what I was doing while you were working on your investigations. I spend almost all my time filtering around the classroom. I eavesdrop on the group's conversations, and I will regularly engage them. Say, okay, what did you figure out for this question? What's your rationale? So I'm going group to group, and I'm interviewing them. We'll also stop the classroom and say, okay, we're going to spend 2 minutes talking about our results here. What did you find? What did you find? What's our consensus? Oh, okay, we think this is happening. And so this is the big picture, and I hope to formalize it for them. So there's many different techniques that we use to make sure they're getting it. And one of them is the multiple choice questions that we've been asking. So you can say, okay, right at this point in the lesson, we were just talking about parallel circuits maybe. All right, grab your multiple choice letters. And you get an instant picture of how your students are doing with that topic. I can see some of you are keen. Let's try it. So grab your multiple choice letters, put them face down once you've decided. I'll give you a minute to look it over carefully. Okay, please make your selection. And eyes to the front, please don't look around. And hold them up. Hold them up. Okay, put them face down on your table. So I'm noticing a diversity of responses, and this is very common in the classroom. And so this is what I do. Now we're going to go through a short discussion phase. Now, if you have the pink cards, can you put up your hand? Pink cards. Okay. So in your group of 3, you will be the first one to talk. So you'll reveal your answer. You will share your rationale for it. And then we'll go to blue. And only at that moment do you reveal. Then to white. So you don't know if there's consensus until the last person talks. Please, if you know that your answer is incorrect by the time it's your turn, explain why you chose that. Because the mistakes that we make are a very valuable source of learning. And I really stress this with my students. Share with your neighbors the understanding that led you to the answer, because that's probably an idea that's circulating around their heads that just might not have popped up that time. So learning from the mistakes is extremely valuable. So we're going to go pink, blue, white. Only reveal and talk when it's your turn. Go.
I think I need your
And what just happened here is a great example of what happens in our classes. A lot of heated discussion, and everybody's personally invested in their answers, and the amount of tutoring that's taking place. When you have to explain your ideas to somebody else, think about this is a great way to learn. Now, please choose your letters for what you think is the correct answer. So you're allowed to change, of course. And eyes to the front, please don't look around, and hold them up. Thank you very much. Thank you. So, and I often give the students some feedback. You know, the class score, the first time that I held it up, was probably about 50% correct. And now, it's almost 100%. That's what I see happening in my class. You see the range go from there to there. So you've had a good chance to talk this, so I won't talk anymore about them. So just to wrap things up, sorry, so a few other questions there. Now, if this is something that you're interested in trying out, don't feel that you have to start from scratch. All my materials, my handouts for the students, my PowerPoints that I use in my classroom, this presentation are available on my website. The URL is at the top of the page, on the first page of the booklet that I handed out. So go to my website. So you'll find my grade 11 physics book. So if you go to the electricity section, a huge part of our electricity unit is review of grade 9 from the very basics. You'll probably find that a lot of it you can directly apply to your grade 9 classroom. If you go to my presentation page, you'll find the link for today's presentation. So click that. You'll get this PowerPoint plus electronic copies of the handouts and a few other goodies that I didn't want to use the paper on. And if you go to classroom videos, you'll see videos of me teaching my class. I don't have the electricity unit up yet, but you will see this inquiry-style classroom in action. And you'll see how I lead it, how the students behave, and I provide pedagogical commentary as part of the videos. So please feel free to look at that. So I wish you the best of luck with your experiments with inquiry-based learning, and physics teachers are awesome to hang out with. We encourage you to join us at Laurier in May for our Physics Teachers Conference, where we're talking about diversity in STEM, in the STEM fields and STEM education. There was one on each table, but I have a few extras if other people are interested in picking this up. So thank you very much, ladies and gentlemen. Had a great time today. And if you could, please tidy up the baggies of equipment and put the materials back in the baskets. Thank you very much, everybody. And I'll be around to answer your questions.